is an absolute pleasure to be able to speak to you all again at GopherCon EU. One day, I hope to actually make it to a GopherCon EU in person. Wouldn't that be grand? So this is a talk about something that Go doesn't have because we don't need it. And because we don't need it, perhaps some Go programmers, you may didn't notice it's not there. And because this absence can sometimes go unnoticed, perhaps they don't know why this is actually kind of a big deal. Now, when I submitted this talk, I was very intrigued by this idea of a vintage talk category because if you know me, you know I love to bang on about this period of history. But because this is a talk about history, it's important to acknowledge that historians, especially amateurs like myself sitting here in this chair, interpret their research through their own biases and their own opinions. And this is especially true of the history of computing, which has such a terribly strong bias towards Western English-speaking protagonists. So, where relevant, I've included some links to the source material using everyone's favorite QR code. So if you're interested, you can do your own research. Now, to introduce this topic, let's start with a little quiz. And I know that this code might look a little bit strange, it's not actually in Go, but there is a point. So what does a simple program print? Actually, because of the magic of virtual conferences, you can't actually answer this. So we'll just keep this in mind, and we'll come back to it a little bit later in the talk. For a second example, what about this program? Does it print true or false? And as the last example, what about this program? We'll print two values here. What are they? So we'll leave the quiz and we'll come back to it a little bit later. Now, numbers are just numbers. You'll never see OXULL in a Go source file. This quote comes from November 2009, which was the presentation that introduced Go to the world. So the first time that most of us saw Go. Now, Warp's pithy line sort of implies that prior to Go, maybe numbers were sort of broken. And if you hadn't figured it out from the samples that I just showed you, perhaps something is broken. So this is where I'm going to start the story. Numbers are just how we measure things. We call these the real ones because they represent real-world quantities. Now, all of us intuitively know that numbers like these are often approximation. For example, 1 1/3, or the ratio of the circumference of the circle to its diameter. And we all know that the temperature of the human body isn't precisely 6.1 degrees. Now, numbers are also how we can count things. These are the integers, the whole numbers, the counting numbers. A farmer, for example, has an integral number of oxen. On census night, there is an integral number of occupants living in that household. And when we write a for loop, we go around that loop a whole number of times. Now, I'm starting here because, in part, this is where the history of computing started. Computers we recognize today evolved, at least initially, along parallel lines. Well, on one, you have computers designed to solve complex differential equations, like the loft of a projectile across a battlefield or the implosion of a sphere. And these are the great scientific computers like ENIAC and Colossus and the Harvard Mark I. And in part, these computers thought in real numbers because their forebears, the analog computers, the fire control computer, the early autopilots, thought in continuous values. Now, there's also a lineage of commercial computers that descend from accounting machines whose history begins well before the word computer was co-opted to imply a machine that performs computations. The story of accounting machines starts with IBM, more or less. And IBM started life as the Computer Tabulation Recording Company, a conglomerate of 4 companies, the most famous of which was the Hollerith Tabulating Machine Company. And we know Hollerith because before that merger, it was the company that was known for automating the US Census using an idea that they stole from the Jacquard loom. So for the first 5 decades of the 20th century, IBM produced back-office counting machines, multipliers, integrators, sorters, collators, punchers. Now, today we think of these as just like functions in the standard library. In the 1940s, each of these functions was a discrete machine through which you'd marshal punch cards to do accounts payable, payroll, stock control, things like that. Now, this is the pre-transistor period, but it didn't mean that we didn't have computation. From relays through vacuum tubes to transistors, the implementation of these digital computers we already recognize is binary. A value that is transmitted between two parts of the computer is one state or another. It's a high voltage or a low voltage. It's a pulse or it's the absence of a pulse. But this doesn't imply that these computers operated on numbers or communicated with their users in binary. ENIAC, for example, was approximately a decimal machine. So in this photo, Esther Gershon and Gloria Gordon are programming ENIAC by connecting these things called digit trunks, these big heavy cables that each contain 10 conductors, one per digit. Now the Horrick punch card operates in decimal. And so even when it was extended to cover not just the numbers 0 to 9, it was extended to cover characters and punctuation. If you look closely, you'll see that in any column, no more than 3 holes are punched. And there's a good reason for that. If we try to represent binary on this card, you could easily imagine patterns where every hole is punched. That card would be a colander. It would be too flimsy to fit through the machine. So even though we think of the punch card as the data storage medium of the 50s and the 60s and the 70s, it wasn't binary. The hugely popular IBM 1401 used this quite strange system called quibinary, where you have each decimal digit is stored in 6-bit in such a way that only 2 bits are on at any one time. And this was a kind of parity checking. And that idea itself descended from possibly the prototypical relay computer, the telephone exchange. So the point of all this is, while it's universally accepted today that computers operate, every computer that we know, from the smallest microcontroller to supercomputers, we think of them operating exclusively in bits and bytes. Back in the 50s and the 60s, this period where formative programming languages were being created, the idea that computers operated in powers of 2 on 8, 16, 32, 64 binary bits isn't anywhere near as settled as it is today. Now, just as a string of letters we know in English as the word, in computers, we say a string of bits is a word. And so the word size defines the largest discrete value a computer can operate on. So if you're an architect back in the 60s and you're building a computer, what you thought about primarily was its word size. To take an example from the time, the 7070 series of commercial mainframes stored its data in words of 36 bits. But the marketing called this out as 10 decimal digits plus a sign. Why 10? Because that was the number of the digits their mechanical counterparts offered. If you're an accountant or an actuary in this period, you might have one of these on your desk, a Marchant or a Freedom mechanical calculator. And if you look very closely, you'll see they have 10 rows of 10 digits. This is a decimal computer, or a decimal adder. So all of this led to a very common word size amongst commercial computers. Those that did accounting and inventory and payroll and all those kind of businessy type things. They were all 36-bit machines. 36 bits is enough to count to a few billion, or to store 6 uppercase characters in a word. It's pretty convenient for doing accounting and printing reports. Now, meanwhile, in the other arm of evolution, in the scientific domain, if you use 36 bits, that gives you maybe 7, maybe 8 digits following the decimal point. Now, perhaps that's good enough for high school trig, but it's not enough for handling large values that differ by tiny, tiny amounts. Say, for example, orbital velocity. So one of the major differences between process control computers, accounting mainframes, and scientific computers was their word size. And just as an aside, like, I have a 30-inch monitor, but I got nothing on this gentleman. So let's take a break from the history of computers architecture and talk about literal constants. Let's get us back to the point. Literal constants are surprisingly complex because they have to be a textual representation of a value in memory. This is super important. Constants in Go source code are the results of evaluating the characters in the source file. When I'm assigning the result of evaluating the expression 1, which is evaluated to itself, and I assign that number to x. Now, the reason I'm belaboring this point in Go, the simple statement that when I write 1 in the source code, I want 1, that number on the page, is just a number. And the reason that I'm belaboring this point is this is a departure from Go's ancestors. And to understand why that is, let's go back a little bit. We need to talk about C. If I write a little program in C, the types of A being obvious, you see it right there on the left-hand side, they're int. But perhaps the better question is, what is the type of 1, 2, and 3? It turns out they have a type, and that type is int. So let me ask another question. What is the type of 10 billion? What is the type of 2 shifted to the left 33 places? What is the type of 8,192 cubed? And it turns out that, again, the answer is int. And this is a problem because 10 billion doesn't fit into an int, nor does 8 billion, nor is 56 billion. And to make the matter worse, int isn't actually a fixed size. So it's not strictly correct for me to say to you that 10 billion doesn't fit, because sometimes it does. And so to understand why constants have types in C, we need to go back in time a little bit further, to BCPL. In 1966, Martin Richards wrote a language called BCPL. It was a stripped-down version of the combined programming language. He wrote it for a specific machine. Now, one of the simplifications that BCPL had was that it had exactly one type, a string of bits, the word that we've talked about before. Everything in BCPL is a word, nothing larger, nothing smaller. This is kind of complicated for two reasons. Because as I've kind of gone through up to this point, the native word size of a computer is strongly influenced by its application. Different computers for different markets have different word sizes. And also, being restricted to a word meant that you weren't able to operate on values smaller than a word. But BCPL is important because it was the predecessor to B. And B is this interesting language that was the result of Ken Thompson's attempt to squeeze a copy of a language that Doug McIlroy wrote called TMG into the tiny memory on that PDP, the first PDP-7. Now, in a presentation at VCF East 2 years ago, Thompson actually claimed that he was trying to write a Fortran compiler. Nevertheless, the result is that B can be thought of as C without types, or more accurately, it's BCPL squeezed through 8K and filtered through Thompson's brain. And this is according to Dennis Ritchie's in his memoirs about the development of C. So the chronology goes that B begat a language called New B and then C. And so specifically when Unix moved from the PDP-7, which was an 18-bit word-addressed machine, to the PDP-11, a 16-bit byte-addressed machine, B, the cut-down version of BCPL, evolved into C, the language that we all know today. And amongst many of its innovations was that C introduced two integer types. We have the eponymous int for the 16-bit word, which is the native machine size of the PDP. We have this new type, char, which is an 8-bit byte. And the name is strongly influenced by the the main purpose of this type, which is to hold arrays of characters, strings. Now, this growth of data types for characters from 6-bit in the 36-bit machine eras to 8 bits was heavily influenced by the development of ASCII, which was kind of happening around the same time, and further influenced by the decision of IBM to stylize on this 8-bit byte for their line of 360 mainframes, which came out about 5 years earlier in the 1960s. So this brings us up to a speed from a historical point of view. And the two takeaways from this point are computers evolved from word address to byte address. They stopped thinking about just single words in memory to talking about bytes, collections of 8 bits. And the second one was they evolved various word sizes initially because of their application or the precision of the calculations they needed, but later it would allow them to address larger memories. So this brings us back to the question, when we can now answer, how large is that int? And this is where things get tricky, because initially int, as we saw in that paper from 1974, was 16 bits because that was the word size in the PDP-11. But then Unix was ported to the Interdata 732, a machine actually here in Sydney was where one of the first ports happened. The 732, as its name suggests, was a 32-bit machine. This made something of a problem, because if int was redefined to be 32 bits, what do we do with the 16-bit quantity that now doesn't have a name? And the opposite is, if we leave int as 16 bits, we need a new name for the 32-bit quantity. Well, as it turned out, the people doing the port just decided that int was going to be 32 bits, and they made up this new type, short, which was for the 16-bit, now vacant 16-bit type. But it gets more complicated again, because while these byte-oriented machines are growing in popularity, the investment in the old word-addressed mainframes, they cost millions of dollars, long leases. They weren't simply going to be discarded. And so by the time we get 4 years later to 1978, Unix and C have been ported to a bunch of machines that have a bunch of different word sizes. It is mostly 32 bits now, except for where it's 36. This is kind of how things mostly stayed for the next 20 years. And I do apologize to the microcontroller users here. I know that in your world, int is 16, sometimes 8. Like, this is kind of the point. So now when we get to the 1990s, and 64-bit machines are just starting to appear, there's a problem, because so much software has been written in C, or translated into C, or implemented in virtual machines that are written in C, that it's all but assumed that while int was intended to be the natural word size of the machine, as it is in Go, for compatibility reasons, it was stuck at 32 bits. So now we can answer some of the questions we opened with. The value on the left, 4 gigabytes, might be defined to be a 64-bit quantity, but the value on the right is an int. And int is assigned 32-bit quantity, and 1 shifted to the left 32 bits does not fit into 32 bits. It's 1 with 32 zeros after it. So on my machine, this prints 0. Note this program. Does it print true or false? It turns out that on the system I have, it prints false, because the value assigned to X is slightly larger than 2.114 billion. It's just a few larger, and what happens when you have a signed integer? It wraps around into negative value. So it actually turns out that X is minus 2.1 billion something, which is less than 0. And its last example, the first print actually prints minus 128, because again, char is signed. Why is it signed? Well, because int was signed. It seemed like a good idea at the time. And also, if you go back a few slides and read, you'll see that they didn't really care about the top bit in ASCII. ASCII was assumed to be 7 bits at the time, so it just didn't really care about the top bit. The second example, And so because this is a signed example, 128 is one too large to fit into a signed 8-bit integer, so it wraps around. The second example, again, 256 is one larger than can be represented in 8 bits, so it's truncated to its lower 8 bits, which are all 0. So these integer literals are all evaluated as signed positive integers, because that represented the word size at the time. Seemed like what I'd do back in the 60s. But later, larger types were added. So you have the situation where you have a computer that can operate on larger numbers that you can type in your source code program. So this means integer literals in C are kind of mess. And they sort of work for small numbers, but the larger you get, the larger the risk of truncation and wraparound and awful portability problems. And the fix for this is to add a suffix to integer literals, U for unsigned, L for long, L for like longer long. How do you know which one you need? Well, again, it depends. How many bits is int on your machine? That's kind of the answer. So this is precisely what Rob was talking about when he said, you will never see OX80 ULL in a Go source file. Now, when you mention a number in the program literally, you write the number 7 in your source code. Eventually, that literal will be assigned to a value, and a value has a type. So maybe it seems natural to assign all literals a type. They're going to get one eventually, so why not do it early? But we saw the results of this kind of thinking. So there you go. The question was asked, well, what if numbers by default didn't have a type? What if a number in the source code was just a number? For example, one shifted to the left, 32 bits, is 4 gig, which fits inside an unsigned 64-bit value. So this code compiles and runs fine on all the platforms that Go supports. Here, X is again 2.1 billion, something which is slightly too large for assigned integer on 32-bit platforms, but it fits on 64-bit platforms. So this code works as expected when run on a 64-bit platform. And to give you examples of a case where value doesn't fit into the type, you get compilation failures, not warnings and undefined behavior. Before I finish, I want to mention another benefit of Go's constants. Literals in C have a fixed type. Literals in Go, by default, are untyped. So we say they're just numbers. It's just an integer. It's just a floating point number. It doesn't have a type. It just has a kind. But that doesn't mean we can't give them types. In this example, I define two constants and deliberately give them different types. But because these aren't just kind of bare integers, just characters on the string, they now have a type. The compiler can tell us when I accidentally mix imperial and metric units. And because we've given these types, just like any other type that you declare in your own package, we can give them methods. And so we can do kind of cute things like this, where we can add 5 feet and 26 centimeters converted to inches and print out the result. So I've heard people say quite a lot that C stands for CBE because of its memory unsafety. But right here, this presentation, the inability to do simple arithmetic without constantly worrying that you've got the suffix right or worrying about the hardware architecture that your code is going to run on. And again, I'm really shouting it out to you microcontroller folks, because while it might be assumed to be 32 bits most places, it sure isn't on a microcontroller. This seems like a much more fundamental issue. Now, in comparison, numbers in Go just work, regardless of the type or the machine size. And when they can't, they fail clearly. And this property lets people grow confidence with the programs that they write and to work reliably. Now, the fact that numbers just work often goes unnoticed because just working is what we expect as programmers. We've enshrined this as the principle of least surprise. But this history of how the Algol family of languages got into this hole and how Go dug them out really, I think, deserves recognition. This notion of untyped constants is so pervasive for Go programmers because they just work. Rarely, perhaps, do we stop and recognize the path it took to get here. With that, thank you very much.